Okay, we are rolling on with day 2 of section 1.3, which is all about analytical limits. So yesterday we learned a couple techniques. We talked about the substitution technique, and we also talked about the properties of limits and utilized those properties to our advantage. So how about, well, let's see what's on the agenda today. One is, or step number 2 is factoring techniques. These will work really well on rational functions. So factoring allows us to rewrite the function into a new function that's equal to the old function, except at maybe one point, and then we'll look for factors that can cancel. If using substitution gives you a 0 in both the numerator and the denominator, then you have what we call an indeterminate form, which kind of means like you cannot determine the answer because you're trying to divide by 0. And the way that we can get around this when we're trying to take limits is to try factoring and having a factor cancel with top and bottom. So functions that agree at all but one point, it says let C be a real number and let f of x equal g of x, all for are equal except for at x equals c, where we have an open interval containing c, and the limit of g of x as x approaches c exists, then the limit of f of x also exists. So these two functions agree at every place except for perhaps the point at x equals c. All right, so let's try direct substitution first, which is always our first line of defense. If I can substitute in, I'm going to try. I would get what? 9 minus 24 plus 15 divided by 3 minus 3. On top, I get 0. On bottom, I get 0, which is what we were talking about. What happens when I get 0 over 0? Well, you don't panic because there's actually an answer to our limit. We just have to be a little diligent in finding it. So let's restructure this limit. On top, let's factor it. It factors into x minus 3 and an x minus 5. On the bottom, I have x minus 3. Let's factor this and cancel those two factors. They cancel to 1. And I'm left with the limit as x goes, or the limit of x minus 5. This is what they're talking about. This g function is going to behave just the same way that this f function does. The only difference between these two functions is that they don't agree when the value is 3, because in this function I can't substitute 3. I get 0 over 0. However, in this function I can substitute 3. So as x goes to the 3, we get 3 minus 5, which is equal to negative 2. And this theorem here says, you know what? That's good enough because f of x is going to behave just like g of x everywhere except just at c, where it doesn't exist for the limit, or for the function. But the limits will exist because the limit is looking at what is happening from the left as well as the right. And in that case, these two functions behave identically. So the answer is negative 2. All right. Letter B. I see difference of squares on the top, but you know, would I even have to plug that in or factor that? First, try substituting the value. Negative 2 squared minus 16 over negative 2 plus 4 gives me 4 on top minus 16 over 2. Negative 2 plus 4 gives us 2. 4 minus 16 on top is negative 12 divided by 2 gives you negative 6. I didn't get zeros, did I? We could actually just keep substituting away. So just because you see that it can factor does not necessarily mean you must factor. The only time you have to factor is if you get 0 over 0. I feel like there should be, oh, we'll just go on to the next ones. Um, Still looking at this factoring technique. If I plug in 4, in this case, I get 4 cubed minus 64. 4 minus 4 turns out to be 0 over 0. And then you're like, what? Well, we actually can find an answer. Let's factor. Do you recognize this as a difference of cubes? 64 could be written as 4 to the third, correct? And difference of cubes have a nice factoring pattern. It goes a minus b. Perhaps you even remember this. That would be awesome. A squared plus ab plus b squared. There's the factoring when I have difference of cubes. Sum of cubes also has a pattern. It goes a plus b, and then a squared minus ab plus b squared. So those are good ones to remember. And that allows us to do some factoring here with this difference of squares that we're faced with. I'll have x minus 4, x squared plus 4x, because it was a times b, remember from their pattern up there. I was on that term, wasn't I? And then plus last thing squared. My b value is 4, so b squared is 16 divided by, well, looky there, x minus 4. X minus 4 will divide into x minus 4, and it generates this new function for us that will behave like our original function as far as limits are concerned. So let's plug in the 4. We get 4 squared plus 4 times 4 is 16 plus another 16. Looks like we got 16 times 3. Answer turns out to be 48. D, what happens if we put negative 5 in? Try it out. 2 times negative 5 squared would be positive 50. Negative 5 times 9 is negative 45 minus 5. Well, I can see 0 on the top. Negative 5 squared is 25. Minus 10, minus 15. That 2 is 0. We get 0 over 0, which means, hey, keep going forward because there probably is an answer to this. So let's try factoring. The limit as x goes to negative 5. I know these are no fun to factor, and they do cause people some headaches, but they are just kind of fun puzzles. 2x squared, prime number, it has to be 2x times x. 5 is also a prime number. That could only be 1 times 5. I just have to get my two numbers in the correct position. I'm going to put my 5 out at the end here. That allows 2x multiplied by 5. I need that to be positive and this one to be negative. I'm going to have x plus 5 and an x minus 3 on the bottom. Check out the foiling. I think you'll see that it is all working out for each of those polynomials, top and the bottom polynomial. Now, x plus 5 divided by x plus 5 gives me 1, and we will try using substitution. 2 times negative 5 minus 1 on top, negative 5 minus 3 on the bottom, negative 10 minus 1, negative 8. Final answer will be positive 11/8, because the negative over negative cancels. Okay, for the last really fun technique called rationalizing technique, we know that if we get 0 over 0, we should try, if substitution gives us 0 over 0, we should try factoring, because factoring is a little bit easier than this technique. If factoring doesn't work, I might be dealing with a rational function that has a radical present. And if that's the case, we're going to use this technique of rationalizing the function to find its limit. We'll multiply by the conjugate of the expression containing the radical. So when I look at a, let's try plugging in 0. If I plug in 0, I get 0 over 0, which indicates to me that an answer is possible. I just have to find the right technique to get around the 0 in the denominator. Well, my radical is sitting in the numerator, so that's where my eyes are going to go and be focused on. This says try multiplying by the conjugate of the expression containing the radical. Well, the conjugate of my radical will be square root x plus 4 addition instead of subtraction there. And this turns to addition now. That's how we make the conjugate. And then an x plus 4 plus 2. Let's multiply. Let's multiply the numerator by foiling. Numerator. And leave the denominator alone. And you'll see why in a minute, okay? So you may want to just write those down to help remind yourself that we are doing this on purpose. We're going to FOIL out the top and we're going to leave the bottom in a multiply, in a factor mode. So let's rewrite our limit as x goes to 0. Multiplying the top will be a FOIL. I'll get square roots times square root. That will give me x plus 4. The inners and the outers, I'll get a positive 2 square root of 4 and a negative 2 times square root of 4. That will zero as a sum between those two. So there is no middle term. And then let's look at last times last gives me negative 4. Divided by, here's where we said leave the denominator in this factored mode. On top, 4 minus 4 goes to 0. And I'm left with just x on top. I have x over x times that other factor. Well, if I have multiplication there in the denominator, that means I can take x divided by x, reduce it to 1, and now let's swing into substitution mode. So plugging in 0, I have a 1 on the top, and I'd have a 0 plus 4 under the radical, and then addition of 2. 1 over 2 plus 2 is 1/4. We did get an answer. It wasn't too bad. The math is a little crazy, but certainly doable. Nothing that you haven't had to do in your previous math classes as far as working with rationalizing out a term. All right. Okay, so let's go on to problem B, get a look at it, and I hope that you start catching on to, you know, the flavor of these. So here is our problem. Let your eyes travel to where the radical resides, because that's going to be where you want to focus your attention. It helps you determine what to multiply by. I guess first I probably shouldn't skip that step about checking out 9. If I throw in 9, I do indeed get 0 over 0. And that's not helpful, is it? Other than telling me there is an answer. So I guess there's a bright side to it. Let's multiply by the radical. So square root of x, change this to a positive so that we're doing the opposite. What we're really generating here is a difference of squares. You know how we have a squared minus b squared? Turns out to be a minus b, a plus b is the factoring. We'll take a look at this. This is a plus b here, and this is a minus b. This is nothing more than a difference of squares where we get first thing squared minus last thing squared. And that helps us out tremendously on these problems. So when we say we're multiplying by the conjugate, what I'm really doing is making a difference of squares factoring. Just thought you'd want to know that. All right, so there we've got it set up. Why is this okay? Because it's nothing more than 1, right? If I simplified the fraction there that we introduced, it's really I'm multiplying by 1. I'm going to come down below. So the limit as x goes to 9. On the top, now this time I'm going to leave it alone on top. I know that's different than the last one, but on the bottom's where it's going to turn out pretty because that's where we have the difference of squares. So foiling this out, I get square root of x times square root of x gives me x. The middle terms, check them out. I'd have a negative root x and a positive root x. Those add up to 0. I'll even write them for you if you want to see them. Just as a reminder of why they're disappearing on us. And then last times last, negative 3 times positive 3 gives me 9. Notice these middle terms do exactly what we thought. They zero out. All right? Now, the reason I said leave the top alone this time is because once I multiplied, once I foiled my bottom, I get an x minus 9 over an x minus 9 factor, and that reduces to 1. This boils down now to a nice limit, the limit as x approaches 9 of the square root of x plus 3, allowing us to use substitution, getting an answer of 6. Sweet! Letter C. Once again, is that not the same problem? Nope, a little different. Okay. Once again, ooh, double radical. That should be fun. My eyes are traveling to this bottom. How about yours? That's where the radicals reside. If I threw in 0 or 3, I do get 0 over 0. There's an answer out there, just got to find it. So let's multiply by the square root of 3 minus the square root of x, square root of 3 minus square root of x. When I multiply, I want to use the radicals to FOIL and leave the other alone. So this will turn out to be the limit as x goes to 3. Let's leave the top alone. That generates this factor of x minus 3 and a factor of square root 3 minus square root x over square root 3. Oops, I got FOIL. Square root 3 times square root 3 generates 3. The middle terms are going to, oh my gosh, you guys, the middle terms wouldn't go away the way I have it written because I forgot to change my sign over here. So let's fix that guy up. Now proceeding. Now my middle terms will go away, won't they? I'll have this negative square root of 3x, and the outers generate a positive square root of 3x, which sum up to 0, so my middle terms are gone. Now on to last times last, we'll create a negative x. Wow, I almost blew that. Okay, this isn't as pretty as last time. And the reason I'm looking here, I've got a factor of x minus 3, and on the bottom I have a factor of 3 minus x. But the cool thing is that this 3 and this 3 are opposite in sign, and the x's are opposite in sign. And if you recall doing these in algebra, when you factored, there was this clever little trick that we could do. I'm going to rewrite my top. The clever trick. Let's factor out a negative from this. So I factor out a negative, and that would make this negative 3 positive x. And then, you know, addition, we can change the order of addition. It's commutative, that commutative property. So I end up with this. And that's going to be pretty nice because I can now take the factor of x minus 3, cancel it with the bottom factor of x minus 3, generates 1. And my answer can be calculated by substituting 3 in. I'll get square root of 3 plus square root of 3 divided by this -1. Don't lose track of that. Up on top, apples plus apples gives us more apples. So I have 2 of those square root of 3's divided by -1, which makes -2 root 3. Beautiful. I believe this is our final one. Excellent. Let's finish it because this is getting to be sort of a long video, but we'll wrap it up. Multiply by the conjugate because when I plug it in, I do indeed get 0 over 0. So multiply the conjugate. X plus 1 plus 2. Hey, I made the right choice there, didn't I? I have to change this negative to a positive in order to get this technique to work correctly. Now, the limit as x goes to 3. First times first will give me x plus 1. The radical times the radical will become squared, and squaring the square root will cause it to go away. Then I get last times last will be -4. Middle terms, of course, had gone away. On the bottom, we do not want to distribute and make a mess of our bottom. So we'll just rewrite those 2 factors and leave them like that. On top, let's simplify out the math. 1 minus 4 makes this an x minus 3. And that is super helpful because now I have the x minus 3 factor canceling the x minus 3 factor, leaving us with the limit as x goes to 3 of 1 over the square root x plus 1 plus 2, 1 over 3 plus 1 is 4, square root is 2, I get 2 plus 2, we get 1/4. Hey, this one we have a little picture on. As x heads to 3, from the left and from the right, it does indeed look like we're at about 1/4, doesn't it? So, picture agrees with our analytical skills. The homework is going to be this page 68, 45 through 56 all. Have fun with it. I would use a separate sheet of paper because as you can tell, these do take a bit of handiwork. Good day.